Today, we're diving into one of the biggest puzzles in the tech world. How do you find that one golden needle of information in a haystack the size of a mountain? Seriously, think about it. We're practically drowning in data. From medical scans to cybersecurity logs, there's just so much of it. But hidden deep inside all that noise are the few crucial little signals that can predict a disease or, stop a massive cyber attack. The real question is, how on earth do we find them?
Well, for that answer, we're looking at some really brilliant research coming out of the International Birch University from Dino, Keco, Zerina, Masetic, and Jasmin, Kevric. They came up with a fascinating way to slice through all that digital clutter, and it all starts by facing a giant roadblock in computer science.
That roadblock has a name, and it's a pretty dramatic one: the curse of dimensionality. It's this idea that as you add more and more variables or dimensions to your data, the problem doesn't just get a little bigger, it explodes exponentially. It gets so big, so fast that it becomes basically impossible for any single computer to solve. So, how do you beat a curse like that? The strategy is something called feature selection, and you can think of it like an expert chef tasting ingredients. Instead of throwing everything into the pot, you pick only the ones that add the most flavor. By feeding a machine learning model only the most important features, you make it simpler, way faster, and a whole lot smarter.
Now, when it comes to finding those best features, one of the top-tier tools is the genetic algorithm. It's fantastic at sniffing out the best possible combination of variables, but, and this is a huge but, it has a major flaw. It is painfully slow, and it eats up a ton of computing power, which kind of makes it useless for the giant data sets where we need it the most.
So how does this thing even work? Well, this is the cool part. It literally mimics Darwin's theory of evolution. It starts with a whole population of random possible solutions. Then it tests each one for fitness. How good is it at solving the problem? It takes the best ones, lets them breed to create a new generation of solutions, and then does it all over again. And with every cycle, the solutions evolve and get better and better.
And this is where the genius idea from our researchers really clicks. They asked, why run this slow process on just one computer? What if we unleash it across hundreds, maybe thousands of machines in the cloud, all at the same time? The difference is just night and day. You go from a slow, bottlenecked process to something that is lightning fast and can scale up pretty much infinitely.
The secret sauce that makes all this possible is a model called MapReduce. It's what powers huge platforms like Hadoop. And the best part is how it works. You can imagine it taking one gigantic, impossible job and dividing it up among a whole army of computers that all get to work on their little piece at the same time. It's really just 3 simple stages. First, the map stage hands out a small part of the job to every computer in that army. Then, the shuffle stage gathers up all their individual answers and gets them organized. And finally, reduce combines everything into one single final answer. It's an elegant way to make an impossible task totally manageable. Okay, so the theory sounds great, but does it actually work in the real world? Well, the researchers put it to the ultimate test on a really critical problem, trying to classify different types of cancer using a massive data set of gene expressions. And get this, for just one of the cancer types they looked at, the algorithm had to sift through over 12,000 different gene features. I mean, that is the curse of dimensionality in a nutshell. A gigantic, messy pile of data with a life-saving answer hidden somewhere inside. And here is where you see the magic. After running their supercharged parallel algorithm, it whittled those thousands and thousands of features down to just about 20. It found the tiny handful of genes that were the absolute best predictors of that cancer type. Incredible. And here's the kicker. Using only those 20-ish features, the machine learning model could classify the cancer types with 100% accuracy on most of the test data. So it didn't just make the problem simpler, it solved it perfectly. Perfect accuracy is amazing, but what about the speed? Remember, the whole reason we're doing this is because genetic algorithms are normally so slow. Well, on a single computer, this analysis took about 86 minutes. But when they split the job across 4 parallel workers, they slashed the time to just 38 minutes. This proves it works. The more computers you throw at it, the faster you get your answer. Now, to prove this approach wasn't just a one-hit wonder for medical data, the researchers applied the exact same method to a completely different world: cybersecurity. This time, they used it to hunt for the key signs of a hacker trying to break into a computer network. And the results? They pretty much speak for themselves.
The best methods before this topped out at around 89% accuracy, which, don't get me wrong, is pretty good. But with their new method, these researchers boosted that accuracy to over 90%. Now, that might not sound like a huge jump, but in cybersecurity, every single percentage point can be the difference between catching a threat and missing it. So, what's the big takeaway from all of this? I think it's the incredible power you get when you mix different ideas together. You take an algorithm that's inspired by Mother Nature, you supercharge it with the raw power of cloud computing, and suddenly you can start solving problems that seemed completely out of reach just a few years ago. And hey, don't just take my word for it. In their own paper, the authors conclude that their method isn't just a cool idea. It's been proven on two very different and very complex problems to work better than anything else out there. That's a huge stamp of approval for their approach. And that kind of leaves us with this really exciting question to think about. We've seen this work for cancer research and cybersecurity, so what's next? What other massive, impossible problems in fields like climate science or financial modeling could we crack open by pairing the beautiful logic of evolution with the unstoppable force of modern computing? The possibilities are, well, they're pretty mind-blowing.